To define the trigonometric functions of any angle, including angles less than 0 degrees or greater than 360 degrees, we need a more general definition of an angle. We say that an angle is formed by rotating a ray, and we'll just call it ray OA, about the endpoint O, called the vertex, so that the ray is in a new position. Right? So in other words, right here, there we go. Right here is ray OA, and we can rotate that ray. Right? I kind of show you with my pen, but you can't see it. Right? So you're just rotating, you're just turning the ray. Right? So imagine this is, just like a stick, and you're moving the stick in a circle. Right? So the ray OA is called the initial side of the angle, and ray OB is the terminal side of the angle. Right? So now we're going to create angles by rotating a ray. So now we can rotate it. We're not limited now to just 90 degrees. We can keep on rotating it and make larger and larger angles. So we denote the angle formed by this rotation as angle AOB, or simply angle O, or even just O. Right? So now we're going to be looking at creating angles on the coordinate plane. And this is in your notes too. So if the rotation is counterclockwise, we say that the angle is positive. And the angle is negative if the rotation is clockwise. Right? So you have this in your notes. Matter of fact, not only once, but twice. I don't know why twice. So if we're moving clockwise, right, just like the clock, right, that's going to be a negative angle. And if we open counterclockwise, that's going to be a positive angle. And it has to do with the way that the quadrants are labeled on the coordinate plane. So positive angle opens counterclockwise, negative angle opens clockwise. We can now define the trigonometric functions of any angle in terms of Cartesian coordinates, not just coordinates on the coordinate plane, points on the coordinate plane. So recall that the xy coordinate plane consists of points denoted by pairs, x, y, of real numbers. The first number x is the point's x coordinate, horizontal position, and the second number y is the y coordinate, vertical position. Together, they determine the point's position in the plane. All right, so here I have 4 points. Notice they have different signs. The xy coordinate plane is divided into 4 quadrants. We have the first quadrant, second quadrant, third quadrant, fourth quadrant. Notice they're named counterclockwise. We go counterclockwise to name them. The signs are just based on the signs of the values in that particular quadrant. So in the first quadrant, both x and y are positive. So there you can see 2, 3 graphed. And you have this exactly in your notes. In the second quadrant, actually I didn't give you the points, but I gave you this part here, the signs. All right, so here, right, x and y are positive. In the second quadrant, the x is negative, but the y is positive. In the third quadrant, both x and y are negative. And in the fourth quadrant, the x is positive, but the y is negative. Right? And that's whether we're above or below the x-axis, above to the right or to the left of the y-axis. Right? And you know all of that. Right? But so now we're going to have our ratios might have a sign to them. So before when we were dealing with triangles, everything was positive, right? Because we're just dealing with lengths. Now that we're on the coordinate plane, notice that sometimes our horizontal or vertical distances could be negative. And that means our trig ratios are going to be negative too. All right, so we can let theta be any angle. We say that theta is in standard position if its initial side is in the positive x-axis. So this is always going to be the initial side. Right, so always measure it from the x-axis, and then we'll see how far our angle turns to get to the terminal side, and this is the terminal side. I'll just put terminal. I can't fit side in there. All right, so we could pick any point, x, y, on the terminal side of theta, a distance r greater than 0 from the origin. And notice that r is the square root of x squared plus y squared. Right? Well, why is it x squared plus y squared? Right? That's the distance formula. Or it's Pythagorean theorem, right? Because we would have a horizontal distance and a vertical distance, and look there, we have a right triangle. So distance formula is just based on Pythagorean theorem. It's always going to be a positive number because it's a hypotenuse of a right triangle. It's part of the circle equation of the radius of a circle, and Pythagorean theorem distance formula. So we're always going to have a positive number, and this is why it happens to be the square root of x squared plus y squared. Right? And it's a positive number because this one is a distance. It's the only one that's a distance. The x and y are positions, and they can be positive or negative. But our radius, or hypotenuse here, is going to be the distance. All right, so three different things that, three different reasons why we use that formula for our radius. Right? And if you remember, it's part of the circle equation for the radius of the circle. That's how we got the radius. Pythagorean theorem and distance formula. And it's a hypotenuse of a right triangle. All right, so let's take a look at how we do these. All right, so for angles in the coordinate plane, we're going to draw a right triangle with angle theta such that x is the adjacent side, y is the opposite side, and r is the hypotenuse. All right, so here we have this above is shown which quadrant the angle will lie in for angles greater than 90 degrees. The angle theta will always be positioned near the origin. And the adjacent side is always along the x-axis. And the opposite is drawn. Sorry, the opposite is drawn. Let me show you where I'm in the notes. The opposite side is drawn from a point perpendicular to the x-axis. All right, so we can draw angles on our coordinate plane. Right? And so it's 90 degrees to the y-axis. It's 180 degrees. Actually, so this is 90 degrees. This is 180 degrees. And if I go that's supposed to be a circle. 180 degrees if I go to the x-axis. If I go back to the other side of the y-axis, it's 270. And if I go all the way back around again, that's a circle. The most horrible looking circle I've ever seen, but it's a circle. All right, so general definition of trigonometric functions. Let theta be an angle in standard position. Let xy be a point where the terminal side of theta intersects the circle x squared plus y squared equals r squared. The 6 trigonometric functions are defined as below. So you have this in your notes. I would write, if you can fit it in there, I'm sorry it's small. If you can fit it in there, I have something written in red, right? And that is which sides we use for all of the different trig functions. Right, so you could think of it two different ways. You could think of it as which value you use, the horizontal or the vertical, or you can think of your position from theta. Right, so sine theta is y over r, because y is the opposite and r is the hypotenuse. Y will always be the opposite, right? Because the angle is nestled in next to the x-axis. Do you see theta there, right? And the x-axis there, right here. See right there, there's theta. There he is. All right, so he's nestled next to the x-axis. So x is always going to be adjacent. Y is always going to be opposite. And then, of course, the radius is the hypotenuse. All right, and that's what we get using the distance formula. All right, so cosine is going to be x over r, or adjacent over hypotenuse. Tangent theta is going to be y over x, opposite over adjacent. Secant theta is going to be r over x, hypotenuse over adjacent. Cosecant theta is r over y, or hypotenuse over opposite. And cotangent theta is x over y, or adjacent over opposite. And the reciprocals aren't exactly next to one another because it's sine and cosecant that are reciprocals, and cosecant, or I mean, excuse me, cosine and secant are reciprocals, but that's okay. I'm just going to move that out of the way. They're sometimes called circular functions. Well, you can see, right, we're rotating an angle in a circle, right? And so not only is that r here, the hypotenuse of the triangle, it's also the radius of a circle. And there we go. So this is in your notes. It's the bottom of the second half of the page. Look at that. We finished the whole page. So, and it really isn't too bad. Right? If you can remember the steps and you pay attention, it's really not complicated. So the steps to find trig ratios given a point. You're going to graph the point if it's not already graphed for you. You're going to draw the reference triangle. When you draw it, you're always going to go straight to the x-axis. So the opposite side is a line perpendicular to the x-axis, and the hypotenuse is a line from the point to the origin. Right? So you're going to draw one line from the origin to whatever your point is, and then you're going to draw another line from your point vertical right down to the x-axis. You're going to use Pythagorean theorem to find the missing side. The missing side, by the way, is going to be your hypotenuse. Because you have the point, you know x and y, which is also equal to r. Right? Same thing. That's always your missing side. So if you want, you can put that right in your notes. And if it doesn't even fit, you can put underneath and just draw an arrow. There's nothing else going on this page. And then you're going to use the reference triangle to find the trig ratios. Okay? So now if you turn the page, we'll be doing that. See, this is going to be easy, cheesy, lemon squeezy. You'll see. So I think I have like the first one or two already done. All right, so if we're going to let negative 4, 3 be a point on the terminal side of an angle theta in standard position, evaluate the 6 trigonometric functions of theta. And by the way, I don't really care if you draw the circle for this. It's totally up to you, so long as you draw the triangle correctly. I don't really care about the circle. All right, so we graph the point, negative 4, 3. Right? And so then we're going to draw a line from the origin to the point, and then draw a line perpendicular right to the x-axis. It's a good idea to label your sides, so you don't get them mixed up. Right? So we've got our point there. This is our x and this is our y, and we can use that to set up our ratio. Right? But in case, it might be a good idea to also label it, on the triangle as well. Right? So this would be the negative 4. That's the x. This would be the 3. Right? And then you use Pythagorean theorem to find the value of r. Right? Don't forget to square the negative. So we have negative 4. The square root of negative 4 squared plus the 3 squared is going to equal the square root of 25, which is 5. Right? Or you could just set it up, negative 4 squared plus 3 squared equals r squared, right? And take the square root afterwards. Right? So you'd have 16 plus 9 equals r squared, 25 equals r squared, and you only want the positive because this is a distance. So it's the only one that's a distance. So 5 equals r. Right? So however, either you do it as Pythagorean theorem or you do it as a distance formula, it's the same thing. Doesn't make a difference. All right, so now all we have to do is write our trig ratios. Reduce and rationalize if possible. All right, so sine is going to be y over r. So it's going to be 3 over, and let's put r on there too. So r was 5. All right, so this is going to be 3 over 5, and then we'll do cosine. Cosine is going to be negative 4 over 5. So you notice cosine's negative, right? Because it's using the x, and the x is negative. Don't drop that negative. Right? Otherwise, it's wrong. Tangent is going to be negative, so it's 3 over negative 4. It doesn't matter where the negative is, so long as it's negative. Right? And so cosecant, I didn't put the, I guess I did the 3 principles and then did the 3 reciprocals. So cosecant is r over y. Right? So that's going to be 5 over 3. That one's positive. Secant is r over x. Right? So that one's going to be 5 over negative 4, and it doesn't matter where the negative goes. And then cotangent, the reciprocal of tangent, is going to be negative 4 over 3. So you can just use your reciprocals too, right? Because cosecant is going to be the reciprocal of sine, and secant is going to be the reciprocal of cosine, and cotangent is going to be the reciprocal of tangent. Okay? So notice which ones, instead of noticing which ones are negative, let's notice which ones are positive. Only sine and cosecant. So we're in the second quadrant, sine and cosecant are positive. Y is positive, and R is always positive. We'll review that at the end. It's not on this part of the lesson, it's going to be on the next part. All right, let's graph the next one. All right, this one's already up there, and this one is, I think, is also in your notes. Yep, it's in your notes, and everything's up there just the same way it is in mine, except there's no triangle. So this time let's draw the triangle in. All right, so the triangle goes, we're going to draw a point from the origin to the point, right? And do your best to make it straight. Oh, and these ones we should graph on a coordinate plane. Now that one is really kind of fuzzy as a coordinate plane, but these ones we're going to graph on a coordinate plane because there actually are points on a coordinate plane. Right? There'll be other things that we may not graph on a coordinate plane. All right, so there's our triangle. Right? So the x is the horizontal, that's negative 8. The y is our vertical, that one's 15. And then we use Pythagorean theorem or the distance formula, they're both the same, to get our r, or our hypotenuse, however you want to think of it, which is 17. All right, so now all we need are our ratios. All right, so sine is y over r, so that's going to be 15 over 17. Cosine, x over r, negative 8 over 17. Tangent is y over x, so that's going to be 15 over negative 8. Cosecant, just the reciprocal of sine, so that's 17 over 15. Secant, reciprocal of cosine, is 17 over negative 8. And then cotangent, reciprocal of tangent, is negative 8 over 15. And that's all there is to it. So you're just graphing a point. You're using Pythagorean theorem, distance formula, to find your hypotenuse. And then you're writing your ratios. Right? That's all there is to it. It really is. So we're going to do a few more. We're going to breeze through this one. All right, so this one is not in your notes because in the rest of them we're going to graph. All right, so we would need to find, I'll just do this as Pythagorean theorem. All right, so we would have negative, oh, R is already on there, never mind. R is 13. It's a Pythagorean triple. All right, so remember we draw our triangle, goes from the point origin to the point, and from the point to the x, right? Not the y, but the x. Okay, go up or down. All right, so negative 5 is the x, y is negative 12, and the hypotenuse is 13. And this one didn't have the distance formula on it. I probably erased it, but that's okay. So here, just in case, negative 5 squared plus negative 12 squared, which would be 25 plus 144, which is square root of 169, which is 13. Okay, that's how we got it. All right, so now let's write all our ratios in. Y over r is going to be negative 12 over 13. Cosine is x over r, so negative 5 over 13. Tangent is y over x, so that's going to be negative 12 over negative 5. Two negatives, those negatives cancel. That's positive 12 fifths. Cosecant, reciprocal of sine, is 13 over negative 12. Secant, reciprocal of cosine, is going to be 13 over negative 5. Cotangent, reciprocal of tangent, is going to be 5 over 12. Let's take a look. So now we're in a different quadrant. Who's positive? All right? The only two that are positive are tangent and cotangent. Well, why are they positive? Well, x and y are negative. So anybody who uses x and y is going to be negative unless you use both x and y, because they're both negative and the negatives will cancel. So just tangent and cotangent in the third quadrant are going to be positive. And we're moving along. I think this one's in your notes. Yep. So this is what it'll normally look like when it's not graphed for us. All right, so we graph our point. All right, 4, -8. So 4, -8 is down here. Am I in the right spot? 1, 2, 3, 4, yeah. All right, so, well, here, let me be a little bit better about that. Let me go through the steps correctly. So 4, -8, there's our point, all right? We're going to draw our reference triangle. So essentially, our angle is coming all the way around to this point here. Okay, that's our point. Our reference triangle, okay, goes, and I don't care if you draw that circle part. I do care that you draw from the origin to the point, and from the point back to the x-axis in our right triangle, our right angles there. Okay, that's just showing you that we're rotating an angle. All right, it's not just a triangle, because later on we're actually going to be figuring out things about ratios for the angle, and the angle is technically this thing that I just drew. All right, this thing here, that's actually our angle. It's more than 180 degrees, more than 270 degrees. All right, and we'll talk about that later. So technically that is an angle there, but we're using a reference triangle right here. So maybe we should draw an angle just so that you kind of key into that later on. All right, so we have our triangle, and now we're going to use Pythagorean theorem to find our missing side. All right, so horizontal was 4. This point here was 4, -8. The vertical was -8. All right, so we have the r is the square root of 4 squared plus -8 squared, which is not a Pythagorean triple. 16 plus 64, which is 80. Right? And we want to simplify the radical. Right? So I'll give you a hint. The largest perfect square was 16. 16 times 5. So I could break this up in a whole bunch of 2's, but instead, why don't we just break it up into 4's, because 4 is a perfect square. So 4 comes out of the radical, 5 stays in. All right, so we do have to simplify our radicals if possible. All right, so now we want all of our ratios. All right, so this is x and this is y. All right, so we have -8 over 4 square roots of 5. Oh, and look at that. It could be it could reduce, and it should be rationalized. We got to do both. All right, if I'm going to move this thing. Oops, no, not that thing. Oops, I think I'm stuck. All right, you know what? Because I really need the space. All right, so if you're okay with how I got this, and if you're not okay, then ask me in class. I'm going to get rid of that. I really need the space. All right, so now we'll reduce. That's a 2 and that's a 1, right? And then we have to multiply by the square root of 5 over the square root of 5 to rationalize. All right, so this is going to be 2 square roots of 5 over square root of 5 times square root of 5 is square root of 25, which is 5. Right? And so if you haven't figured out the pattern, you will. All right, it's just going to be, when you're rationalizing a radical and it's a square root, it's just going to be the number under the radical because you're multiplying it by itself. Okay? All right, and so, let's go over to cosine. Oh, and look at that. Our point is right in the middle of it. It could sit over here, go over here. Move, move, move. All right, so cosine is the x. So that's going to be 4 over 4 square roots of 5. Again, that'll reduce. I figured out why I don't have enough. I can barely reach the board. I'm all tangled up on my cord. All right, so this cancels 1 and 1. And then we'll rationalize square root of 5 over square root of 5. So that's going to be the square root of 5 over 5. All right, so now tangent is y over x. So that's going to be negative 8 divided by 4, that's an easy one, negative 2. Cosecant is just the reciprocal of sine, right? We're just going to flip them. I'll write it as before it's reduced, right? And then we'll just reduce it, right? So this would be 4 square roots of 5, right? Because it's the r. So I want to make sure you understand where everything comes from, right? And then over negative 8. Right, so now we wouldn't have to rationalize it anyway. That would just reduce. That would be the square root of 5 over negative 2. Right, and then secant, reciprocal of cosine, is going to be 4 square roots of 5 over 4. That's going to reduce. You can see why I wouldn't just want to use 5 and square root of 5, because then I'd have to rationalize. Right? The 4's will cancel. Square root of 5. Cotangent, reciprocal of tangent. Right? So now that's going to be 4 over negative 8. Which is negative 1/2, or 1 over negative 2. Either way is exactly the same thing. I want to make sure I don't confuse anybody. Whoops, spinning ball of death is never my friend. What the heck? They just changed the page? Let's go back, come on. There it is, okay. Can I erase? Just didn't really seem to want me to erase. All right, 1 over negative 2. There we go. So this one wasn't in your notes, but it's the next one. I hope the next one's as good as this one. Of course, if this one the next one doesn't have rationalizing, you might want to just change the point and come back and copy this one, right? Because you could just rewind me. All right, so now let's move on to the next one. That's one of the benefits of me having me taped. Do all kinds of things. You can rewind me, you can stop. We're almost done. All right, negative 7 and negative 4. Oh, by the way, I forgot to mention who was positive. All right, so in this one, who is positive? Notice it's cosine. Oops. Well, you're positive if I forget to draw your negative in there. Anybody else? No, everybody else got their negative. All right, so positive, cosine, and secant, right? Because they use the x value, and the x value is positive. Tangent and cotangent use x, but they also use the y, which is negative. And of course, sine and cosecant use the y, so they're negative. All right, so this one here, negative 7, negative 4, or in the third quadrant again. Probably should have put that other one in your notes. All right, there's our point. Right, so our angle starts here, right, and we're rotating an angle. I don't know where exactly to put it over there to make it perfect in a circle, not this horrible looking thing, but you get the idea, hopefully. All right, so we draw a line from point to the origin and point back to the x-axis. All right, and then let's find the length here. So r is negative 7 squared plus negative 4 squared, which is, I don't even think this one simplifies, 49, I think it's probably an ugly number, and 16. All right, so that's going to be 65. Yeah. And it doesn't simplify. We were better off with the other one. All right, 5 and 13. See, it doesn't simplify. So that's going to stay square root of 65. What a lucky one. So if you don't like this one, and you like the other one, they're both just as good. You could change the point and just go copy the other one. But anyway, since we've got this one up here, we may as well do this one. Not a very pretty point. This is the square root of 65. All right, so x and y. So r is kind of, doesn't even simplify. All right, so sine theta is going to be r, and so that's, I'm going to come to my negative there. So it's going to be negative, so remember this one's the negative 4, probably should do this. This is the negative 7. So negative 4 over square root of 65, and we'd have to rationalize that. Nothing to reduce even. So negative 4 square roots of 65 over 65. Cosine, we'll use the x. That's negative 7 over the square root of 65. You can see I just made these numbers up. I just chose this point at random because this is kind of big numbers here. So negative 7 square roots of 65, I have to say this 6 times, over 65, and that's kind of sloppy. I was hoping this would be less than 30 minutes, but it's almost done. Tangent is going to use negative 4 over negative 7. So once, I'm not going to have to use that square root of 65. 4/7. Cosecant is in the reciprocal of sine, right? So it's going to be square root of 65 over negative 4, and that's all we have to do there. Secant, reciprocal of cosine. So that's going to be square root of 65 over negative 7. And cotangent, the reciprocal of tangent, is 7/4. And there we go. And again, tangent and cotangent were positive. And everybody else is negative. All right, moving along. So this one's in your notes. You can copy this one down. You rationalize if there's a radical in the denominator. Nobody cares about a radical in the numerator. It's got to be somewhere. Can't get rid of it completely. All right, so this one is in your notes. It's actually a pretty easy one. We're going to graph our point, 3, 0. So now look at our angle. There it is. There's our angle. You might say, how do I get a reference triangle out of that? You got an x, you got a y, you got a reference triangle. Nobody said it has to look like a triangle. Sometimes they don't look so triangle. Here I got nowhere to go, so obviously I can't draw anything. I can't draw a point. I drew the point from the. I drew a line from the origin to the point, but that's it, right? I don't have any vertical distance to draw back to the x-axis. So let's find our r. R is 3 squared plus 0 squared, which is going to be square root of 9, which is 3. Surprise, surprise, the length is 3 units long. How could we have guessed? All right, so sine, so I got nowhere to put the r, but it's over here. I have nowhere to put it on the triangle, on the quote-unquote triangle. So sine is going to be 0 over 3. That's 0. There's no vertical. Cosine is going to be 3 over 3. That's 1. Tangent is going to be, so tangent uses the y, it's going to be 0 over 3. That's 0. Cosecant is the reciprocal of sine. It's going to be 3 over 0. Guess what that is called? It's called undefined. Secant is the reciprocal of cosine, so it's still 3 over 3, which is 1. And cotangent is the reciprocal of tangent, so that's going to be 3 over 0, so it's undefined. Now look at our values here. We get 2 1s, 2 0s, and 2 undefineds, right? And there we go. That one's all done. And actually, those are important values. When we go to graph later, sine and cosine, the fact that sine is 0 when I haven't moved anywhere, and cosine is 1 will be important. We're not going to graph the other ones. If you notice, undefined, undefined, what might those have? Can you guess? Cosecant and cotangent have vertical asymptotes right there at that point 0. So, but anyway, moving along. And so we can get our ratios even when we don't really have much of a triangle. We're going to do the same thing now for 0, negative 3. So now I am down here. Right, so, oops, come on. Everyone wants me to finish. All right, so right now, let's put 0, negative 3. So I've done what I can in terms of a reference triangle. X, Y. Do I really need to tell you that R is 3? It's still a distance of 3. Right? Sine is going to be negative 3 over 3. That's negative 1. Cosine is going to be 0 over 3, that is 0. Tangent is going to be negative 3 over 0. It is undefined. So now we know that tangent has vertical asymptotes as well. Cosecant is the reciprocal of sine. That's going to be 3 over, actually it would be 3 over negative 3, but either way it's negative 1. And then secant is the reciprocal of cosine. That's going to be 3 over 0. It is undefined. Now you know that the graph of secant has vertical asymptotes, and cotangent is going to be the reciprocal of tangent, 0 over 3 or 0. So now we have 2 that are negative 1, 2 that are 0, and 2 that are undefined. And so if 3, 0 is on the terminal side of the angle, theta is 0 degrees. If 0, 3 is on the terminal side of, if 0, 3 is on the terminal side of the angle, then theta is 90 degrees, right? So this is my theta. I have no, on my first one, I have nobody even put theta, right? So this is 0 degrees. Here, this is my theta, right? So that's 90 degrees. Right, so that's why we can evaluate, right, for on our x and y axes, even though you can't really make a triangle, right, because we still have an amount of turn. You can turn nothing, right? We can evaluate any kind of angle at all. Come on. If we have negative 3, 0, right, we've gone 180 degrees. And if, so this would be theta right there. And then if 0, negative 3 is on the terminal side, we've gone 270 degrees. If we keep on going, we go back to 360, which is the same as 0. And you can just keep going around the circle many, many times. So quadrantal angles, that's a mouthful. That's a nice tongue twister. Quadrantal angle. So it's an angle whose terminal side falls on an axis. So example, 0, 90, 180, 270, 360. You can just keep going around the circle. 450, 270, 720. Right? Just keep going around the circle. We'll work more with angle measures in the next lesson. Says, remember their names? This one was Melvin and Philippe. And Philippe says, I can't wait. I hope you can't wait either. All right, so see you in the next podcast. Bye for now.